All right.
We're learning about waves.
Module 9. We're learning about waves and sound.
I thought we were learning about sound waves.
Sound waves, waves and sound. Yeah, that's it. You got it. Okay, here we go. Is this our first blank in the book? A mechanical wave is a disturbance in matter that transfers energy through the matter. Do you have to write that whole thing down?
Yep.
Woo. Sorry about that.
Can I write it down?
Are you pretty quick at it though? Some people aren't as fast as writers as other people, so. So what was the disturbance in this matter? What was the matter here? Water. What was the disturbance?
Droplet.
A drop. And notice how the waves are going out in concentric circles. Interesting how it always does that. As long as it's free, you know, if there's if you drop it near the edge, it'll hit the edge and it'll stop. It'll make the complete circle, right? That's a drop all the way up there. So you see the drops, and that one up there. When it gets to the top, just before it falls back down, it's gravity free for that split second, and then boom, then it goes.
It brought sand and droplets up with it.
Say again?
It brought more droplets up with it, looks like.
Yeah. So several of them come in. It's really kind of fun to watch water droplets in slow motion, and how when they get to the top and they have no gravity, they're a complete sphere, right? And so that's kind of cool. When they're not affected by gravity, they're a sphere. If we have water droplets in space, they're a complete sphere. It's pretty cool stuff. All right, we good? Okay. So types of mechanical waves, we have a transverse wave and a longitudinal wave. All right, and so we're going to see a transverse wave is this one on the top that looks like a wave, for instance, a wave we might see in the ocean. The waves going up and down like that, right? And then the longitudinal wave, it's harder to draw this right here. It's harder for you to see what's happening here. It's really like a circle. Think of this one like a slinky. All right, and I'll show you some examples of that here in just a second. We're going to draw a transverse wave in a minute. You have a box.
The wave's not going up and down, it's going side to side.
It's going exactly right. It's not going. It's going perpendicular to the energy.
It looks
versus
the same
parallel.
as that one.
I know. It looks just like a small. So it's hard. It's just more difficult to draw that one right there, which is why we don't draw it. So we are going to draw this one, however. So you have a box to draw a transverse wave in. Mm-hmm. Yeah, this one I just put it up here bigger so you can see it a little easier.
That's what I always draw.
Oh, do you?
You never know you're drawing it. You always do.
All right, so you have the top of it's called the crest. The bottom of it's called the trough. Okay, and have that line going through the middle right here. From that middle line to the crest or that middle line down to the trough, those are called the amplitude. Sometimes they'll show the amplitude going all the way from the trough all the way to the top of the crest, and that is incorrect. It's from that midline going up to the crest or down to the trough. And then from trough to trough or crest to crest, we have something known as a wavelength. Now these words are going to translate over to our other type of wave, which would be a sound wave, but it's not as easy to draw that. So this wave is not a sound wave. This is a wave, for instance, of light, a wave of water, ocean wave. So energy waves, ocean waves are energy waves, and they're transverse waves.
What's an equilibrium?
Equilibrium will be when it gets right down to here, right here to this equilibrium line, if you will, right in the middle. It's neither going up nor going down. It's at equilibrium. It's up and down, equally up and down.
I've already learned all of this.
Because you read it all already.
Yeah.
Good.
It's
Well, you
not
can
a
catch
review.
me if I mess up on something. Sometimes I say the wrong words, right? Sometimes I just make stuff up. I don't know.
Because you don't have the book.
Speak with authority. I do have the book at home. I do. Yeah, I don't think I could get through this without the book because it changed so much between last year and this year. All right, does everybody have a thing drawn with the things labeled on there? Got our amplitude, our wavelength, our crest, our trough. You don't have to write equilibrium, that's all right. Okay, but I do want those things. I want you to know those things. In fact, those might be questions that might be on a quiz. Okay. You might have to draw a transverse wave on a quiz. All right, a medium must be present. Now, when we get to sound waves, okay, a transverse wave, well, I'm going to take that back. Light is weird, and it may travel in waves, it may travel in packets, we don't know. We don't know what it's doing. But what I do know is that light can travel through a vacuum, but sound cannot. Okay? All right, so a medium must be present for sound to travel. So it has to go through something. Right now my voice is going through the air and it's being picked up by your ears, okay? So that's the medium through which my sound is traveling. I'm vibrating air through my vocal cords.
What?
And y'all can hear it. Hopefully y'all can hear it. The medium could be a solid, liquid, or gas that sound can travel through. So for instance, if I knock on the table, and if you put your ear on the table, you would hear it coming through. You ever seen those movies where they put their ear to the ground to see if maybe the horses are coming or the train is coming? Or that's actually true. I'm going to show you a video here in just a minute. It's pretty cool that shows that. All right, so we can't, because sound is energy waves, these energy waves, this type of mechanical energy must travel through a medium. Light is different. It's energy, but it's radiant energy, not mechanical energy. Okay, so that's why it's different. So in a vacuum, where we have no air at all, sound cannot travel. So you've heard stories about sound. You can't hear a sound. You can't hear somebody scream in space or whatever. How does it go? Right? You can't hear a sound in space. That's true. There's no sound in space. There's also no combustion in space because there's no oxygen. Right? So that nothing can burn. So something could explode, but there would be no fire associated with it because it doesn't have any oxygen, and you can't hear it go kaboom. So some of those movies when they show it burning and kaboom and that kind of stuff out in space, totally wrong.
So it would just be like a voice?
Yeah.
That's like
Yeah, it could still explode if I had the right kind of detonator, whatever.
So that's
that
how
didn't.
you know that if you watch a movie about space, it's not real.
Right.
In space.
Right. Yeah. There's a lot of things in movies that I sit there and go, nope, that doesn't happen. You know. All right. So interestingly, when we talk about how quickly sound can travel, it actually travels the slowest through the air. The way I'm talking to you right now, the way we receive most of our sound through air is the slowest, least efficient way for sound to travel. All right. Now, our ears, of course, are made to pick up energy waves, sound energy waves, from the air. That's how our ears are, designed. So if we go underwater in a pool and somebody makes a sound, you can hear it really well, right? Clink, clink, something like that. But our ears, of course, would prefer to hear something not underwater. Okay, so it's muffled, if you will. And then a solid is the best.
Quieter sounds.
Say again?
You hear quieter sounds?
It depends on what the sound is. If somebody is clinking spoons under the water, you can hear those really well. If it's metal on metal like that. Okay, can sound travel through space? Here we go. An astronaut in space shuttle. Okay, so I couldn't quite get what was happening in this picture. I thought the space shuttle was going to hit the guy. I thought it was like a collision situation happening. No, there's some sort of little explosion, I guess. Oh no, a meteoroid, asteroid hits the space shuttle. Okay, so the astronaut in the space shuttle, he hears it. See, he turns around and goes, "What's that?" This guy can't hear that. He's just like, "Ooh, I love floating in space," right? Can't hear anything. There's air in the space shuttle for the sound to travel through. The astronaut on the spacewalk can't hear it because there's nothing between her and the impact to carry the sound. All right, so we have something here.
Hi, I'm Andy. I work at Edwards Vacuum, and I'm here in our Global Technology Centre in the UK to demonstrate that sound doesn't travel in a vacuum. I've got a vacuum pump, a bell jar, an alarm, and a microphone to demonstrate that the sound level will drop in the vacuum. So let's set up the experiment. I'm going to place our radio microphone into the bell jar and set our alarm. When the alarm goes off, you'll hear it. It'll be very loud. Okay, I think I can just about hear that, but you'll be able to see on your screen a visualization of how loud it is. So I'm going to suck out the air from this bell jar, close this valve so that the air can't get in, and open this valve to allow our vacuum pump to suck out the air. The air is being sucked out now, and you should see the sound level dropping on the microphone. So you can see our gauge reads 0, and also the levels on the microphone have completely dropped. That's because a sound source vibrates, and that pushes the air and transfers the vibration to you hearing it. But because there's no air in our vacuum, the alarm is vibrating, but it can't transfer that to the microphone. So I'm going to do the reverse now. I'm going to shut this valve and then open this valve. So the air's back in now and the microphone's picking up the sound and I can just about hear it as well. So that's been our experiment. We've proved that sound cannot travel in a vacuum. If you are going to replicate this experiment, please have an adult present. Thanks for watching.
As if we have a bell jar and a vacuum pump. Yeah. I do have a little tiny vacuum kit, right? We used that already? We didn't use that already? Okay. Anyway, I also have a little tiny speaker that fits in it, except I can't find it, so we can't do that. But I can show you the video I made of that. Yeah, so, because it's got to be able to fit in there. Okay. All right, so that just showed that sound does not travel in a vacuum. Energy can travel in waves. Sound travels in waves through a medium. The definitions of the two basic forms of waves helps us to see the difference between them. So the transverse wave, the one you drew, is a wave which the medium vibrates at right angles to the direction. So that's perpendicular.
So the medium, like the thing that's
The medium is vibrating, the sound, not the sound, whatever's going, water, whatever it is going through that, vibrating at right angles to the direction that the wave travels, and then maybe it'll help you with longitudinal, the wave in which the vibration of the medium is parallel to the direction that the wave travels. It's called a perpendicular oscillation. Perpendicular, the energy's going this way, it's going up and down next to it, whereas longitudinal wave, the energy's going this way, and so is the vibration. We'll see that. I'll show that to you. I have a video next, and then I also have a little illustration. You have enough light? I can turn the light back on if you need it. Are we good? Okay. Let's see what we're talking about here. Okay, so same direction. This is a sound wave. There it goes. See it traveling back as well. Okay, so we have so our sound is traveling like this. The vibration is going parallel with the energy. So the energy's traveling this way, and the vibration's traveling that way. Whereas in the transverse, the energy's traveling that way, and the wave is going up and down. All right, so we can see here when it gets together, it's called a compression, and where it's the farthest apart, so kind of like right next to it, it's called the rarefaction. All right, so we have compression and rarefaction. I think this, I thought this one moved. In a longitudinal wave, the direction of the wave moves parallel to the direction of the oscillation, which is the energy, the movement, or the direction that the wave is going. All right, I have one, here it goes. So notice that these items, the spring is not traveling, it's not going down, it's moving, it's compressing and moving a little bit, but it's not going all the way down, is it? What's traveling all the way down?
energy.
The energy is traveling all the way down. Okay, it's kind of weird to think of it that way. So right now, my voice coming to you, the energy is traveling through the air to you, all right, parallel in this longitudinal oscillation. Okay, now surface waves are different. These are going to be the other ones, the ones that are going. These are the ones that are on the surface. We'll be looking at our longitudinal waves here. Okay, so we talk about surface waves when we're looking at these guys. A surface wave would be a wave in the ocean, okay? But also when we talk about, here they are in the ocean on the right side here. Whenever we talk about surface wave, we also talk about earthquakes. So earthquakes happen deep underneath the surface of the earth, but it sends up energy, and those waves travel through the surface, and they change from deep down in the earth to up on the surface. And there's different kinds of surface waves, S waves, P waves, and those kind of things. We have Rayleigh waves and Love waves, and these are all do kind of little different thing, but each one of them causes damage on the surface of the earth because the earth is not supposed to be moving like that, right? so check these out. So once again, I want you to look at the little red balls here. So they're moving a little bit, but they're not going all the way down, but the energy is moving down. So the energy's traveling down. So the both types of waves are similar in this way. All right, that the energy travels, but the mass of the stuff, in this case air when I'm talking to you, or water when we're in the ocean, it's not traveling. You would think that it seems like the water of the ocean is moving because we stand on a beach and the water comes crashing in on us. But really it's just the energy of the wave hitting the shallow bottom, and it causes it to bump up a little quicker. So if we look at a wave, check it out. Okay, so we're following this little dot right here. Okay, the energy's moving this way, but the little dot's just going up and down. You may have noticed this if you go out to the beach and you go out like to the sandbar or whatever, and you just kind of stand, you're out there in the water visiting with your friends or whatever, and you'll notice y'all are just bobbing up and down. Just bobbing up and down. Because that's what the energy's doing to you. Okay? There are such things as currents and stuff like that that can change some of that, but also the bottom of the ocean changes the way the water breaks on the top. But the energy travels in a circle like that.
Cause when like when I'm in the beach, we're swimming in the waves. We end up further down.
Yeah,
in the
that's a current that's pulling you down that way. Okay, so but it's not the wave energy that's doing that. The wave energy is just going up and down. All right, but the bottom of the water makes a difference. That's breaking waves, and then the wind and the windy days will be even more to one direction. And then the currents that happen, for instance, in the Gulf of Mexico, there's a current that's pulling it down, and that current will pull you, for sure. But the energy itself, while traveling, the mass is just going up and down, and it travels in this little bit of a circle. Notice the smaller circle down here. The deeper in the water, the energy's not as great as it is up on the top. Okay, so wave properties. The amplitude is how high it is from the rest or equilibrium position. That goes from middle line to up or middle line to trough. Frequency and period. Okay, so the frequency is how many waves per second. If I'm standing on the beach and the waves are hitting me, I count how many per second hit me. That's frequency. Then we have wavelength. That's the distance from crest to crest or trough to trough. They're the same. That's called the wavelength. All of this is going to be important in a minute when we have to apply a little bit of math to this. All right, wave speed. Wave speed can be calculated mathematically, and I put this hooray person in there. Hooray! We get to have math problems again.
Do we have to write down those 4 things?
They are fun.
Do you have to write down these 4 things?
Yes.
Yes. Where are they? Little boxes or something?
On the
Yeah.
bottom.
On the bottom. Amplitude, how high from rest position, frequency and period, how many waves per second, wavelength, distance from crest to crest, or trough to trough. You can just write crest to crest. So when we talk about wave energy, we often will show this sort of wave right here because it's just easier to comprehend it in our head versus the longitudinal wave, which the slinky going back and forth. That doesn't make as much sense to our brains, at least not to mine. So that's why we like to use these up and down waves like this. All right, are we good? So we have 10 in this class. Okay, so I'm counting 9. Okay, all right. So here's our equation. Let's write this down. Our speed of the wave. Speed equals wavelength times frequency. Wavelength is this lowercase Greek letter L called lambda, and just F for frequency. Okay? So the speed is the wavelength from crest to crest times the frequency, how often they're hitting me, right? And those are going to be proportional to one another. All right, here's an example. One end of a rope, if we take a rope, like if you're holding a jump rope and I start doing this, it's going to make some waves, right? Is vibrated to produce a wavelength of 1.2 meters. The frequency is 3.3 hertz, that's 1/seconds. Did we talk about Mr. Hertz? We did, didn't we, Mr. Hertz?
It's in the book.
What is the wave speed? I should have put him in here, I thought we mentioned it before. Okay, so we're just gonna use this right here. We have the frequency and we have the wavelength. All we have to do is plug those numbers in. So the speed equals, are we doing V for velocity?
39.6.
No, V is speed and velocity, so they just do both in one.
I just have a V over there, no one. Speed equal wavelength times frequency, it says V.
Because V stands for speed.
I know. So I thought for velocity. 1.2 times 3.3 is 3.96 meters per second. What did it ask for? What is the wave speed? Okay, good. 3.96 meters per second. Was that wasn't very difficult. Yes.
So, in our engineering class, we were learning something about bridges, but there was something where the bridge went at the same frequency of the Earth,
Oh.
and it started just.
Did y'all see that one, that bucking Bertha or whatever it's called? And it started.
Yeah.
And
Oh,
it
yeah.
fell down. It fell
Oh,
down.
yeah.
Yeah, you got
there was
it
like, there was like a car with a dog inside of it.
on it
Yeah.
when it fell down.
Unfortunately.
Oh,
No. Whenever
Only a
it
dog?
was waving, just so the guy tried to save his dog.
But the guy wasn't in the car.
No, he wasn't.
But the dog was.
Who died?
Dog.
Haven't got it?
Yeah, the bridge broke with the car and dog on it.
It was that famous one up in New York, like Washington State, that was just like, I mean, you can watch it.
I
Just do
think so,
this
yeah.
crazy looking, and it had to do with frequency, right? It had to do with the frequency of the material being used for the bridge, I guess.
Yeah, the wind matched the frequency of the bridge.
Yeah. Yes.
for my birthday, I went to a city and I saw a dog riding on the hood of a car.
In a cage
No, it was just sitting on the
on the
hood
roof of a car.
Was it
Yes.
leashed down?
How fast was the car going?
Nope.
How fast was the car going?
Kinda slow.
So like
wait,
20?
what town? What city did you go to?
It was like the city for my birthday.
But like
What
But
city?
it was very
Austin?
crowded.
Austin.
I think somewhere close to New Braunfels.
Okay. Wow.
That's weird.
I've heard of a dog in the back of a truck all the
I thought
time.
you were talking about like
Some
India
guy
or
had a
something.
snake around his neck.
Oh.
Yeah, how big was it?
That's an actual
It's
pet
getting
or
more
something.
long.
Yeah. Okay, our next problem, 9.1b. What is the
Yellow.
frequency of a wave that travels at a speed of 3.0 meters per second and has a wavelength of 0.5 meters? Okay, so this time we have our, change that to a b. We have our speed, but we don't know our, what are we looking for?
Frequency.
The frequency. We're looking for f, okay? All right, so we just have to move that around a little bit. So we have, there we are, we're looking for our f. So we're gonna solve for frequency equals speed over wavelength. So it's a fraction, right? It's a division problem. So we're gonna see 3 meters per second over 5.5 meters gives me 6.01 over second, which is hertz. So 6.0 hertz. I need to bring in Mr. Hertz
I was
here.
off by 1.
Did you do it in your head, or you had it on your calculator?
Calculator.
Wow. Off by one
the
what?
heck?
6.1?
I had 6 point 0.
It is 6.0.
When I got it.
6.00, not 6.01.
Oh
That's not a 1. That 1 is
Oh.
is part of the unit, 1 over seconds.
Oh, yeah.
So it's
Oh, I did get it.
6.0. Yeah.
I did get it.
Okay, 6.0 hertz, yeah. So that's why 1 over a second is a little confusing there. We just call that hertz now. So 6.0 hertz is right. Okay, so in summary, frequency and wavelength are related. Speed is wavelength times frequency. And then we're going to just put this over here. F equals V over lambda. We don't have anything else? What if we're looking for the wavelength? Huh. All right, I just put that star, so we need that for when you do have a quiz, not next week, but the week after. We're going to need this formula, okay? I need to know this formula. And there's probably some practice problems in your book, right? Does your book have practice problems in addition to regular study guide?
Yes. Wait. Kind of?
Does it? Okay, I don't
Yes.
know. Does it? Okay, so if it does, I would recommend doing the practice problems. All right, we have the formula written down right here. Boom. All right, here's practice. This is OYO on your own. It says here something about a beach. On the beach, the wave moves with a speed of 0.5 meters per second and has a wavelength of 0.25 meters. If you stood still, how many waves would hit you every second? So what are we looking for? Trying to see how many waves would hit me per second. What am I
That's
looking
frequency.
for? That's frequency. All right, so what's the frequency? So F equals V over lambda, right here. Okay, we have those numbers, don't we? So our speed is 0.5 meters per second, and our wavelength is 0.25 meters. Right there, and it gives 2.0 hertz. So 1 over second. So 2 per second? Is that how that works?
I did not get 2. How did you get 2?
How does it get
I don't know. Somebody else wrote this thing. I didn't check it. Check my math.
0.5 times 0.25 is not 2.
0.5 divided by 0.25.
Oh, it's divided.
Yeah, that's over. That's over it.
But still not.
That's 2, yeah it is.
2. Yay.
Yeah. 2.0.
All right. So like I said, practice problems will help you. On our quiz, we'll have at least one math problem. Probably a couple math problems.
Oh, did I type it wrong?
All right? Okay. Could we say that frequency and wavelength are inversely proportional? Let me give you a hint. Whenever you see something that is a fraction, that means inverse proportionality, or inversely proportional. That means when one gets big, the other one gets small. When one gets small, the other one gets big. Okay? So the answer is yes. Did you have that question in your book?
I don't know what you're talking about.
What are you talking about? We could say
Yes,
they're
that was in our book.
Okay, inversely proportional is, yes, they are inversely proportional. I think the last time we covered this in the last edition of the book, this question was asked, and it got left in there by somebody else. Okay, let's take a look at our sound wave right there. Remember, it's traveling like that, and it's hitting something now, and it's causing that membrane there to vibrate. And that's similar to what's happening inside the ear. Okay? So our ear looks something like this, right? The sound comes into, this is called the pinna, or the outer ear right here. You can live without that if that's not, of course you'd have trouble holding your glasses up, but we don't need this part right here. But what it does is it acts like a funnel. Have you ever, when you're trying to hear somebody do this, it actually just extends your ear and you can hear a little better because it's a bigger funnel, bringing more sound into it. What?
How much better?
Put your hand on your ear. When you hear me, can you hear me better now? Coming to you? Yeah, so if I'm talking to you, it actually does bring it up a little bit. Yeah, it does help a lot. So if somebody's a low talker, you just kind of do that. In fact, if you do that, they'll start talking louder because like, oh, you can't hear me. Yeah. Okay, so the sound comes in, it's traveling in the waves, the energy's going on the way, right? It's going on that longitudinal wave coming in through, and it hits that thing right there called the drum. And the drum, of course, has a membrane, and that membrane starts to vibrate. And then it starts to vibrate these 3 small bones, the smallest bones in your body. Yes?
Say you were to stick one of them, what's it called? Q-tips.
Uh-huh.
How far would it go under your ear? Like,
It can go pretty far. If you have pain after putting one of the Q-tips down in your ears, you've just touched the nerves right around here because you have some very sensitive nerves around your eardrum because it's trying to say don't come any closer to me. Okay, because you can break the eardrum. Now you can still hear if your eardrum's broken, and your eardrum can get repaired. But you'd rather not have to. It's painful, so you don't want to have to go through that. Yes.
Where's 8?
That's a good 1, 2, 3, 4. Where's 5? 6, 7, 9.
That ear is missing part.
I don't know. Good question.
That's a deaf person.
That's a deaf person.
Missing part to the ear.
7.
It's a
I'll
deaf.
call 8 that right there. Okay,
It's
I
a
can
deaf
see.
person.
Well, okay, so I'm going to say that there's 3 bones in here. We have the incus, the malleus, and the stapes. Those start to vibrate. So inside here we have sound traveling through air. Inside here, this is called your middle ear. We have sound traveling through air. Okay, if you've ever gone up a mountain and you have that weird ear popping thing, it's because this little tube right here called the eustachian tube has collapsed from pressure. And so if you swallow or chew some gum it'll open that back up and you'll hear it'll pop and you'll hear the sound come back. Yes.
Yeah, that was my question. It's like, why do you every time you swallow, why is it clear?
Because it's connected to our nasal cavities right here. This is the eustachian tube is connected. So when you swallow, that's why if you're on a plane, they say if you chew gum, you know why chewing gum helps? Because while you're chewing gum, what are you doing? You're swallowing. Okay, and it causes that to open up. Yes.
If you plug your nose and swallow, it also helps a lot.
Or if you plug your nose and just blow, that'll pop it open. Yeah, that'll do
Yeah, I
it
do
too.
that.
All right. So
Well, how come
then,
it does that?
huh?
How come it collapses like that?
Oh, because of the pressure. So if you're outside and there's pressure, like you're going up in a mountain, you have less pressure. That's what happens when you go up in a mountain. You have less pressure, and what happens is the pressure that's been keeping your eustachian tube open has been overwhelmed, and it snaps it closed. Well, it doesn't snap it closed; it just flops it closed.
Hold it.
That bad?
And then restoring the pressure is what brings it back. It's not bad. It's a way to relieve pressure inside our head. So it's actually a little relief valve. Yes.
What is your opinion about cloning?
What does cloning have to do with this?
It doesn't.
Cloning is something that we have done, and I think we probably have to look at
We
the
can
ethics
clone
of that.
people?
Not
Yeah.
people. I didn't say
Sheep.
people.
Cows, rabbits, dogs.
Dolly
Yeah.
the sheep.
You can
Dolly the
clone
sheep.
an animal and they'll have an ear. That's how it
There's a local place in Texas that actually clones dogs and cats.
Dogs, really?
But if you do it with sheep,
Yeah.
Only halfway through the ear.
what else can
There's a
you do?
commercial about it.
Crazy, man.
Yeah.
All right. So we're talking about vibrating here. This is how we hear. We're vibrating. We vibrate the eardrum. We vibrate the three smallest bones of your body, and then it hits this structure right here. That structure has liquid in it. Has fluid in it. Okay. Then it starts to vibrate the fluid. What did I tell you about the vibration of sound? It goes better through fluid, doesn't it? Better. So that means it's going to concentrate the vibrations in this. Now these three things right here, which I'm going to guess are number 7. These are called the semicircular canals.
Number 7 is the cochlea.
I'm sorry, number 8,
5.
number 8, number 5 or 8, wherever those go. Yeah, the cochlea is what does the hearing. Okay, so these things right here, you know what these are for? They're for the other sense that we have in our ears, the sense of balance. So when I bend over like this, those little semicircular canals have a little rock that goes, and it knows that I'm bending over like this, so I don't just fall forward. All right, my body compensates for me bending, so I don't just fall. Yes.
Have you ever got water in your ear and
Uh-huh.
like you turn over, you could hear it swishing inside?
When that happens, the water's stuck right in here. Okay? Not typically here, but if you have a cold, then sometimes fluid will build up in here. And sometimes that'll get infected. Anybody had an ear infection when you were a little kid? Yeah, anybody get the tubes put in the ears?
I did.
Did you get tubes?
I have
You know what
some
that
in
you
my
know what the tube went? It went right here through your drum. Right here. And what that did was anytime you had fluid building up in there, it would just drain out through the drum. And you had to put little earplugs in there to not let water
Did it
get
hurt?
down there, right?
What?
You didn't want water to get down in there.
No. No,
Yeah.
I still can't because they're still in there.
Seriously?
It helps me to hear because without them, everything's muffled.
Interesting. Okay, they put them in to stay? Because typically when you put them in a little baby, my little daughter had them when she was like 18 months old. By the time she was 3, they'd fallen out, and it just closed up
Mine
the
were
eardrum.
permanent because I couldn't.
Interesting. Okay. All right. So this area here needs to be air-filled. That's the way it's been designed. But sometimes the fluid gets in there when we have a cold. That's why sometimes you're like, I can't hear very well. I can't hear. It's muffled. That's because there's fluid inside there. As long as it doesn't get infected, you're fine. Yes.
That's what
How does
it's
it get stuck inside there if it's open?
How does what get stuck?
Water, stuff like that.
Oh, how does it get in here? It's usually from
No, on the other side.
over
On the-
here.
On the canal part, yeah.
Because it's narrow. Yeah, but then if you do this and drop, jump, and it kind of gets almost like, I hate to use the word vacuum because nature abhors a vacuum, but it gets suction, and I hate that word too. But it gets stuck right there, and then you just have to give it a little nudge to get it out of there.
I just hold my head sideways.
So then the cochlea has the vibrations coming through and back out. We're going to watch a video in a second. Here's just a little deal watching the vibration. See, those little bones are vibrating, and they're going to vibrate the stuff inside the semicircular canals. Actually, that's just the fluid that tells if our head is upright. And then, of course, the cochlea. So the cochlea is responsible for hearing. Let's watch a video.
Have you ever wondered how sounds make their way from the source all the way to your brain?
This is
Take a
the
trumpet,
rest
for
of the
instance.
story.
When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates 3 tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea.
Cochlea means snail.
It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Why does it go through her head?
That's how sound works.
Okay, so the speed of sound equation, B of sound, speed of sound is 3.31.5 plus 0.6 times T, temperature, meters per second. So these, I guess these are standards, right? These are going to be, the speed of sound is, depending on the temperature, the speed of sound is constant. It's about 700. Didn't we talk about that? Did we talk about a sonic boom? Oh, we haven't talked about a sonic boom yet?
No.
Those are so cool.
It might be next week we're talking about it. Yes.
What's the T stand for?
Temperature.
Temperature?
David, do you have a question?
Why do you see fireworks before you hear them?
Because light travels way faster than sound. Sound only travels a mere 775 miles an hour, where light travels 180,000 meters per second. Miles per second. Temperature matters. Sound travels faster when the molecules are moving faster. If the air is cold, the gas molecules are not moving fast, and the oscillations are slower. So, on a warm day, the speed will increase. So I think we can calculate, in fact, next week we're going to do that. Next week we're going to calculate the speed of sound in the room at the temperature of the time. So we'll be able to tell what temperature, like right now it says it's 68 degrees in here. That's perfect.
It's hot.
It's cold.
68's about right, yeah. If it's much warmer than 68, I get hot. Yeah.
So,
No.
the warmer the faster,
What?
the warmer it is, the faster.
The faster it goes. Yeah. The faster. But it still travels pretty fast,
And the
775 miles an
sun
hour.
is like,
Yeah, on a hot summer day, it's going to travel faster.
How much faster?
Well, it depends. We'd have to plug it into this little formula right here. Speed of sound is that. Remember distance. Oh, we have to remember this. Probably should write that. These are the kind of things I forget. Distance equals speed times time. Air temperature makes a difference. So we're going to see our speed of sound V is going to be 331.5. Is that what it says? Plus.
331.5 what?
That's a good question.
Times time.
Times, and then this is going to be, I'm going to put a little degree right there like that because that's going to be temperature. Okay? Not to be confused with time. In fact, time should be a lowercase t. And then sound travels faster with warm air. There we go. The temperature is 68 degrees. Oh, that's what it is here. 68 degrees. What is the speed of sound? All right, so all I have to do is I do have to convert 68 to centigrade. So I do have to use the Celsius scale. Centigrade is the same thing as Celsius. So I have 331.5 plus 0.6 times 20 meters per second. Multiply first, then add. So 331.5 plus 12 gives me 343.5 meters per second. Well, what is that in miles per hour? Does anybody know? Anybody got that?
4.
I can ask them to phone.
Well, I don't know what meters, how many meters there are in a mile.
A lot.
5,000 something, right?
Well, I know how many meters are in
Oh,
feet.
you do know how many meters in a mile. What do I have? 343. 343.
No.
2 miles.
It's
Is a meter bigger than a foot?
3,000.
Is a meter bigger than a foot? Yes, a meter is 3 feet.
About like, isn't it? Never mind.
42 meters per second
3,000.
in 2 miles. Well, I'm getting some strange number, like 42,000 miles, which is nuts.
No. That's so weird.
Yeah, I don't get it.
I think.
The speed of sound is somewhere about 775 miles per hour.
I think it's 1,426 meters.
That's
In a
still,
mile.
that's, in a mile. I don't know what it is. I'm very bad at conversions. All right, here we go. Somebody asked about lightning. Oh no, fireworks. Now we'll talk about lightning and thunder. A physicist is watching a thunderstorm. She sees a flash of lightning and then hears a thunderclap 2.0 seconds later. If the air temperature is a cool 15 degrees C, how far away from the physicist was the lightning formed? So we just plug everything in. We already have our temperature in Celsius. We do our multiplication and our addition. So 240.5 meters per second is how fast it's traveling. No, I'm sorry.
I just write this down.
What?
Yes.
I don't know. Do you have a blank for it in your book?
9.3.
You have a box for it? Then don't worry about it.
There's a box of example 9.3.
Oh, then
Yes.
you're supposed to write it down. Let me just check something really quickly.
That's
Okay,
not it.
that's not, okay. So what am I'm finding the speed. So that's telling me how far, oh, here it is. Okay, it's down here, it's right here. So our speed is the distance traveled times the time traveled. And the distance traveled is speed times time. So I have to figure all this out. It was 2 seconds, I have to add that 2 seconds in there, so I get my 240 right there. Multiply it by the 2, so it's 681 meters away. I was about to say, it's not telling me how far away it is. All right, so in other words, I have to use distance equals speed times time, right there, 2. So we calculated our speed, right there.
Thank you.
You get it?
No.
You don't understand it, or you haven't finished writing it?
I'm not sure what we're trying to figure out.
Okay, so we are doing our first this formula, the speed of sound, right, at the temperature, which is 15 degrees, so right here, that first line, V equals 331.5 plus 0.6 plus times 15, and we get up that our speed, V, is 340.5 meters per second. But it's not asking me the speed, it's asking me how far away it is. So I have to come up here and say, well, our distance is speed, which I just calculated, times time. And it did tell us how much time passed, 2 seconds. So I just plugged that in here to distance equals 340.5 meters per second. That's our speed times our time, 2 seconds, I get 681. Now do you get it?
Yeah.
Okay. And this is how practice problems will help you. By practicing these, okay? How do y'all like your math class?
Yeah, it's okay.
That sucks.
Are you doing this kind of stuff, algebra and stuff like that?
Mm-hmm.
Yeah. Okay. Well, so this should lend toward. This should help you understand. In fact, I've had people tell me that using practical things like this actually help with your math comprehension. Okay. So maybe that's what will happen here when you do your practice problems.
It just hurts my head.
Yeah, I hear you. I have a headache too. So math does that to me.
Oh my.
Got it.
All right. Now, just practice, this one says. In a thunderstorm, the temperature is 18 degrees C. If you see lightning flash and hear thunder 1.5 seconds later, how far away is the lightning? Okay. First, we determine speed using this formula here that's given to us. The 18 comes from that, our temperature. We end up with 342.3. Now we know the speed, and we can insert it into the distance right here. And we take that number we calculated times 1.5 seconds, which was given to us. So it's 513.45 meters away. To convert to it, multiply meters by 3.28. Oh, good, that gives us feet. That's how we get feet. 1,684 feet away. That's converting for us poor American minds that need feet and miles and stuff like that. All right, there we go. Here, I have a few questions for you. Does sound travel faster in a solid or a liquid?
Liquid.
Solid.
Hat, she thought you would.
Solid's the
What?
fastest.
What?
Does sound travel faster in a gas or a liquid?
Yes.
Liquid.
Liquid is now the answer for this one. Does sound travel faster in a solid or a gas? Solid. For sure, yeah, okay. So here's our solid, liquid, and gas. You can see roughly it's the slowest in the gas, it's the fastest in the solid. So I've always told students, y'all all know this, if you're trapped in a building, hopefully that never happens to you, instead of trying to yell out help, find something metal to bang on. And they'll hear that better, and then what are you gonna tap out?
SOS.
Do y'all know, everybody know how to tap out SOS?
But what if they don't know how that sounds?
They will.
They do.
They will.
Okay.
Dot, 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 dash, 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 dot, dot. That means help me.
That's what the. I
Save
thought
our
it was.
souls.
You could do a Morse code.
That's Morse code. SOS. Dot, 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 dash, 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 dot, dot, dot.
Then I don't know Morse code.
What exactly is
SOS.
that?
just learned out of history.
Like,
Yeah, Mr. Morse, Samuel F. B. Morse.
so dot and then what's a dash?
Well, so like if you were pushing it on the little telegraph, it would go doot doot. That'd be the dot. And it'd go doot 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 doot. So it lasts longer. So we just go dot dot dot, and then we go, and then
It originally meant save our ships.
or save our souls. And I don't know that it meant that at all. I think it had to do with the ease of doing 3 dots, 3 dashes, and 3 dots. And then we later said, oh, save our souls.
What if you
Save
did
our
that on
ship.
a beach? Like you just,
The first
like,
time it was used
didn't
was on a
touch
ship. The first time it was used was the
Actually on a
Titanic.
beach.
Sinking. Yeah, Titanic sinking for sure. Oh, okay, here we go.
It didn't work.
We gotta watch it. This is a great video, y'all, talking about how, listen, how sound travels through things.
If you don't believe that air vibrates, take a look at this. Sound waves can travel through solid things like wood as well.
Oh, it's gonna be loud for me.
The particles in a solid are packed together far more tightly than air particles. What difference do you think this makes to the sounds you hear? Listening with a stethoscope can hurt. Does sound travel faster in the ground or through the air?
That's it.
And is the speed of sound ever as fast as the speed of light?
Not even close.
To find out, you need to make a sound that can travel a long distance. 5 tons of plastic explosive should do the trick.
I've learned this 5 years ago.
You saw this one?
I know.
How would you detect sound waves in the ground? Samantha's going to watch for the explosion, but she's wearing headphones so she can't hear it. Fung is going to listen for it, so he's wearing a blindfold. And Elizabeth's going to detect sound waves in the ground.
Yeah, it's a piece of metal.
Ready?
Ready?
I don't want that job.
I don't want that job either.
I'm gonna be the one fixing my back.
Yeah, I'll be that guy.
So, who's going to be the first, second and third to detect the explosion?
They're gonna bring the flag down as soon as they hear it, or feel it, or detect it.
waiting to see the light, hear the sound, or feel the sound. Samantha was first because the light got to them before the sound. Elizabeth was next when she felt the sound coming through the ground. And Fung was last when he heard the sound of the explosion coming through the air. The speed of sound in the air is 350 metres per second. At 5,000 metres per second, sound travels much faster through the ground. But light is much faster than any sound, at 300 million metres per second.
Oh, I want to write it down.
What? Huh?
I have
Write
it
that down.
down.
300 million.
Billion.
300 with 9 zeros. Okay, so it is time for lab. Now, I will tell you, we're going to start off here with listening to some music. But we have to see it because I'm going to put it on here. Now, there's an experiment in your book that asks you to try to blow out a candle with sound, but I'm a little convinced that the experiment is flawed.
It is. Sound doesn't have